Hey guys, Mrs. Stans here. So just want to give you a preview of what's to come tomorrow. Tomorrow we will be on lesson 8 and we're going to be solving quadratic equations by graphing. So we're back to graphing. We will be using our graphing calculator and I'm actually going to do the do now with you. So I'm on page 30. We can copy the objective tomorrow in class. Solve the following equations by factoring. That you could do on your own. You could do tomorrow at the start of class. I just want to do what's new to you, which is completing the table of values so that we can graph. Now, actually, completing a table of values is not so new to you at all. We can easily just enter this into our graphing calculator and copy the information from the table feature. So in our y equals, if you have anything there, of course, clear it out. So we'll put in the equation of x squared minus 4x minus 5. That's the equation that was given to us. And since we have to fill in a table of values, I might as well just go look at the table and copy down the information that they want us to do. So negative 2, 7. What was it? Negative 1, 0, and then negative 5. At x equals 1, it's at negative 8, and then negative 9. And then a strange thing seems to happen, where at 3, it's at negative 8. At 4, it's at negative 5. At 5, it's at 0. And at 6, it's at 7. Is this looking similar to any other kinds of functions that we've done? Hopefully you're saying yes. Hopefully you're kind of thinking about our absolute value functions. Now this definitely is not absolute value because there are no absolute value symbols in this equation. But this graph does have a turning point just like our absolute value functions did. If we can plot these, so when I plot, I get this kind of shape. It's not an absolute value. It's not a V-like shape. If you remember with our absolute value functions, the rate of change was the same on the right side of the turning point as it was on the left side. But when I look at this, I can see on the right side it goes up 1 over 1. So I have a rate of change here of 1 over 1. But then the next one is 3 over 1. And then the next one is 5 over 1. And the next one is 7 over 1. So the rate of change is not constant anywhere. So it really doesn't make a V-like shape. It makes a U-like shape. So we will connect these points with a smooth curve. Now with my pen, I actually have a hard time on the computer, so bear with me with my messy V-like, U-like shape. And if you were to look at your table of values, it goes beyond these points. So I'm going to extend and put an arrow. And this is the shape of the graph. I'm calling it a U-like shape, but there's a real name to the shape of this graph. This is called a parabola. Kind of looks like I wrote parabola, but the way you pronounce it is parabola. All quadratic equations make a U-like shape, and that U-like shape is called a parabola. All quadratic equations create parabolas. That is so important to remember. So we know absolute value graphs make a V-like shape. We know linear graphs make straight lines. We know that exponential graphs show a graph that's constantly increasing or constantly decreasing. And now we know that quadratics make parabolas. So very, very, very important. It's asking us to state the interval where the function is decreasing. Remember, to decrease means it goes down when we read from left to right. So it's decreasing until it gets to where x is 2. So it's decreasing from negative infinity to 2 because it's decreasing along this line. And then it's increasing past this where x is 2, so it's increasing from 2 to infinity. Just like in our absolute value functions, this is an important point. It is a vertex, so it's the same name as what it was in absolute value functions, or we can call it a turning point. And we can talk about this turning point being a minimum or a maximum. In this case, it's the lowest point on the graph. Therefore, on this graph, it would be a minimum. The minimum value that it reaches is -9. So these are all vocabulary that you've heard already. It's asking if the function on number C, in choice C, or part C, is the function positive or negative in the interval from -1 to 5. So if I look at my x values from -1 to 5, here's where x is -1. Here's where x is 5. And if I look at the graph between those lines, you don't have to draw these lines. I'm just drawing it so that I can point things out to you. These lines are not part of this function. I'm looking between these lines, though. You could see that the parabola, all of the y values are negative. So when it's asking if the function is positive or negative, it really is negative because all of the y values are negative. This is the part of the graph that falls below the x-axis. And on the next page, they're asking us for some key features. The axis of symmetry, the vertex, which we already labeled, the roots we'll get back to, the turning point we already labeled, the zeros, we'll talk about it, maximum minimum we talked about, and end behavior, which we'll talk about. So let's go look at that graph again. So I want to get rid of these yellowish orange lines that I drew. And so the vertex is that point in which it turns, and that's why it's also called a turning point. And in this case, it actually happens to be a minimum since it's the lowest point on the graph. The axis of symmetry is this line that I'm able to draw where the graph is symmetric. It always goes through the vertex because this U-like shape is symmetric around this line. The vertex always lands on that line. So this line, that's not part of the function that we can draw in if we wanted to, is called the axis of symmetry. When they ask about the roots The roots are the places where the graph crosses the x-axis. So there are two roots for this function. Lots of quadratic functions have two roots. And actually what we've been doing over the last 2 days when we find what x equals, we were finding the root. So the root on this left-hand side is when x equals -1. And the root on the right-hand side is when x equals 5. Roots are always x values. Roots are always visible on a graph because it's where the graph crosses the x-axis. There's another name for a root or another name for this value of x here. We sometimes call it a solution, and we sometimes call it a zero. Remember, we had said that lots of quadratic equations have two solutions. Or we could say lots of quadratic equations have two roots. Or we could say lots of quadratic equations have two zeros. And the reason why they call it a zero is because what we've been doing over the last 2 days, that we've been solving quadratic equations by setting it equal to 0 because we wanted to use that zero product rule. If we use the zero product rule, we know that there are two factors that multiply to be 0, and that's how we find the x value. So that's why sometimes we call them the zeros. It's because we set it equal to 0. It's because the y value actually happens to be 0 at these points. This leftmost point is at -1, 0. This rightmost point is at 5, 0. So sometimes we call them roots, sometimes we call them zeros, sometimes we call them solutions. So sometimes we just call it the x-intercept even. So axis of symmetry we talked about, vertex we talked about, roots we did, turning point we did, zero we did, maximum, minimum, end behavior. End behavior really just means which way is this graph opening. So this is opening upward. So the end behavior, what's happening at the ends, what's happening to the y values at the arrows, it's going off to infinity. If it was opening downward, then it would be going off to -infinity. Again, I'm not too worried about end behavior here in Algebra 1. You will be talking about it a lot, though, at the high school. So that's it for today. I hope this was helpful for tomorrow's lesson, and I'll see you tomorrow. Bye.